Hello, good morning everyone. So welcome to the second day of this celebration workshop. So for the first session we have two talks. The first one is by Luis Ibáñez from Universidad Luis Bonilla. Luis Bonilla from University Carlos III de Madrid. Luis, the floor is yours.
Thank you. Okay, good morning. So it's a pleasure to be here in celebration of Geli's work and lifetime. So I'm going to talk about her years at my university, University Carlos III de Madrid. And okay, so this one is one of the few pictures I got. So you see Geli attempt to discover what mistakes whoever it was talking there was making. Okay, so I'll have very few of them. So I'll start by just remembering how she appeared in my university. She was hired as interim associate professor of applied mathematics in 93, 94, apparently. She immediately got a tenure associate professorship the next year in 94. And in 2007, she left us to become senior researcher here at the Institute for Material Science in Madrid. While she was with us, okay, so she did a lot of things for my group and the departments, successive departments. So during 93, 94, she was coordinator, secretary of the PhD program in mathematical engineering that we started, secretary of the math department in 2004, and she went to a lot of commissions, meetings, and whatnot, because my university is characterized by doing tons of meetings and achieving relatively little in them. Okay, so I'm going to talk about research and teaching and anecdotes about that. So one of the main things is that we started an associated unit with this institute in July 96, apparently, called the Group of Mathematics Applied to Condensed Matter. And originally, there were just Geli and myself on our part, and Paco Guinea and Gloria Platero from the ICMM, plus our different students. Okay? We had many ongoing collaborations on research and teaching at the PhD level. And this is all I'm going to say. So there are many, many works that they did together, Geli, Paco, and Jose Gonzalez. But I remember one of the first ones on Fuller rings, in which they calculated the electronic spectrum in the continuum, approximating the Fuller ring by a sphere with a Dirac monopole at its center. Okay. And so I'm sure that other people have talked about other works, so I'm not going to comment anymore on this. What was the University Carlos III at the beginning? I was there when they opened the School of Engineering with industrial engineering in 1991. And let me tell you what it was. If any of you have watched these Indian movies, like Bollywood, and all of those, there are a bunch of them that take place in Tamil Nadu and other places in southern India. And sometimes you see some high school or university there, and you get the impression of, okay, so a place like that, the middle of nowhere, nothing going on. Okay, so that was 1991. We were occupying a former high school with terrible acoustics, and people had to do all the teaching and so on from scratch. So it was a little bit depressing for, in some aspects. So I remember that I wanted to have some more intellectual life in those years. So I lobbied and convinced people to start a PhD program. And that's this PhD program, Mathematical Engineering, which after having undergone a bunch of avatars, still persists today miraculously. Okay, so let me comment about undergraduate teaching in a School of Engineering as opposed as the same thing at the School of Physics, Mathematics, and so on. Well, my experience is that when I was in a School of Physics, I had to teach sometimes mathematics topics, but we had a lot of academic freedom. Of course, this is years past, because I'm sure that now things have changed a lot. So we were able to design the syllabus to a great extent, because essentially nobody cared, and change topics and whatnot. When we arrived at the School of Engineering, that was a much more rigid teaching. In fact, the system there kind of stifled innovation, even in teaching. For instance, when we started, everybody in physics, chemistry, and so on had to start a laboratory to teach the students, and it was, that's very reasonable, because on an experimental subject, you need the students to learn the chores and to be able to understand experiments. The equivalent of that in teaching mathematics would have been using a computer lab and changing the way these things could be done. Of course, that was impossible to do in this university, even at the beginning. We had an innovation which has been extended to the full of Spain in later years, which was all of these teacher evaluation sheets. So we had them really from the 1990s on, and that one helped to more or less stifle creativity in teaching, and essentially what we had to do was something like training seals. Okay, you get a student to repeat a bunch of things, and it's like what they say in English, training seals. Of course, this has been petrified by ANECA, so now everybody is training seals all over the place. In fact, many of the people in Spain, their idea is taken from a mollusk called the goose barnacle. Okay, so that's percebe in Spanish. So this goose barnacle is an interesting animal. I mean, it attaches to a rock, filters water, eats. So it's born attached to the rock, grows attached to the rock, reproduces at the rock, and dies attached to the rock. So for many people, that's the academic teaching and research ideal in Spain. Okay, so you do the same thing you learn, continue doing the same thing, and die doing the same thing. So with all of that background, it's not surprising that to innovate in teaching is a thankless job in Spain. Of course, I remember that you would devise a course, put a lot of effort in it, taught it, check the teacher evaluation sheets, and you will say that, okay, students didn't like you that much, but they loved the adjunct professor, which in Spanish is asociado. Those guys come from high schools, and I remember Geli had a very straightforward approach to that. So she asked those guys how they did it, and that was it for her evaluation reports. They were fantastic. Okay. Of course, we had other colleagues who, instead of trying to do the hard topics and whatnot. They wanted to do as many easiest topics as possible and waste the least time repeating the stuff every day. Okay, so that was more or less undergrad teaching, not tremendously exciting there. So we started a PhD program in mathematical engineering, which before I started, I went to a bunch of meetings. As I said, in my university, we liked the meetings very much. And I discovered that there was a program in economics, because the Faculty of Economics, Law School, and so on started 2 years earlier than us. And those guys had like 53 credit units. At the time, people in PhD, they didn't have even courses. So they followed the classical approach, like Socrates, Plato, and so on. So each one had a master, and that was it. Master would teach the student what needed to do. And however, these guys in the Economist, they needed to teach some mathematics and quantitative things to the students who came from, oftentimes, from humanities. So they had elementary courses and a lot of courses. So I got the same idea, and we had like 53 credit units in 2 years. And the idea was to teach people coming from engineering, physics, or mathematics, an interdisciplinary formation so that they could tackle problems in different disciplines with a different approach. And here I copied. We had like 20 students, and I remember that there were 3 engineers, 11 physicists, 5 mathematicians, and 1 chemist. We had, after 1 year, we changed the specialties, so they are the ones that you see there. The 2 first specialties, namely fluid mechanics and semiconductor and devices, continued being more or less interdisciplinary. The other one became strongly disciplinary. The program got awards from Spanish ministry and so on. And after '96, of course, the ministry decided to legislate, and they legislated 32 credit units, so we lost half the teaching course. And I remember that Geli was in charge of solid-state physics and quantum mechanics, and sometimes there were very few students, so they were mostly reading courses that I remember. So I said I did some archaeology, so this is one of the things I digged out. So that was the ad for the first year of the program, and it says more or less that. And we had a relation of professors who were all friends and collaborators from other institutions, and some from Carlos III. So I see that when this thing was ordered, I think that Geli was not yet hired. So after this year, she was in all the ads. So she had 3 students in our program, and I have written here, so the first one was José Vicente Álvarez Carrera in '98 with a thesis called Correlated Electrons about Van Hove singularities. Second one was Belén Valenzuela, who is here. Her thesis was strongly correlated electrons in low-dimensional systems. And the last one in my university was Alberto Cortijo about graphene. So Alberto is also here. And after that, Geli had moved here, so her students graduated in Autónoma, I suppose. I wrote, all of the names are in Spanish because in those years we were not allowed to write PhD thesis in English. Okay, so some rules that we had coming from the law school. Yeah, so that was the first rector of our university who was a big name in national Spanish politics. So he was strongly against translating things into English, and this is why these names are like that. So the other thing that we got a lot of help was that we organized some international conferences, and this is one, that's the only thing I got out of this one. And I remember that, okay, so you'll see this a funny composition, oh, sorry. This is a funny composition because, okay, you see this thing is the courtyard of our building. This is one statue that we got from the Museum of Modern Art in Madrid, who is on campus. And then all of this is, of course, Calatrava's buildings in Valencia. So they looked more prettier than the original thing. So Geli organized a big mini symposium there and was part of the local organizing committee, and that's where I got the pictures. Okay, so this is one of the pictures with the organizing committee probably troubleshooting something. I forgot what. This is same thing. And of course, in this mini symposium, there were talks, and I got this picture out, which is a composite, out of them. So, oh, sorry, I just did the, okay, so anyway, that was ferromagnetic carbon nanostructures, and that's the same picture as before, and this is another one that I got with Paco apparently being speaker and sitting down there, so he's ubiquitous, as you can see. Okay, so digging things, I was able to get a bunch of photocopies, which I thought were given to me by Geli, but I'm not sure. Okay, I was unsuccessful getting the picture of Geli with academic garb. No doubt she has it. And other things that I remember very well, but I do not keep a copy or have lost it or whatever. But anyway, one thing that I got was a bunch of photocopies of a booklet, which is kind of interesting, and I copied it here. Okay. I'm not sure that that was given to me by her or not, maybe, because I got the photocopies in the same box. So this is a booklet called Basic Laws of Human Stupidity by Professor Cipolla, who was an economist at UC Berkeley. And the guy said that unfortunately there is always a constant fraction of stupid people, sigma, no matter in which human group, okay? So whether they are cleverer or academically gifted or not, according to him, even Nobel Prizes, you have a sigma fraction of stupid people. And stupid, well, of course, this is mathematics. So this guy got this diagram that you see here. So X is the actions that you do that give you some profit, and Y is the actions that other people do. So you have here intelligent people, so they do some actions that are good for them and also good for other people. Then you have here helpless, that are people that have no clue about what doing, and maybe they help other people but damage themselves to a certain extent. Here you have the bandits, so these guys do good things for them and steal from the others. So perfect ones are the ones that everything they steal, redundant, goes to their profit. Okay. And finally here you have the stupid people, and they would attack you even if they damage themselves. So you cannot, according to this guy, you cannot protect yourself against this type of people. So you can protect from the bandits because you see them coming, but stupid people, you cannot, okay? So theoretically, if you have in a society a percentage of people above this PM diagonal, then the society is more or less prospering. But if you have a predominant stupid people or bandits on the decision-taking things, the thing goes south. Okay, and from what I know and my experience, I would say that clearly Geli belongs to the first quadrant I. Okay, thank you.
Thank you, Luis. So the talk is open for questions or comments that you want to make.
Is it wrong what the value of sigma is?
What?
The value of sigma?
Sigma. The guy never says it. So that's the thing. To give you an idea, I mean, I gave this book to a friend of mine, and from Berkeley, actually, and he said, well, after this booklet, I read again Landau-Lifshitz mechanics, because it's the same authoritative style. However, in the case of this guy, is much more open to discussion. So it's one of the things that Landau said about some set of physicists. I mean, this guy is seldom right, but never in doubt. So.
Okay, thank you, Paco. So, no more comments or questions. Thank you, Luis.
Thank you.
So let's move to the next talk, which will be given by Bruno Amorín from University of Minho, Haga.
Okay,
Thank you, Bruno.
Hi. So thank you for inviting me. I was very happy when the organizers invited me to give this contribution in this conference in honor of Geli. I'm a bit of a hot contribution because contrary to many of the presentations that we had yesterday and today, I wasn't a student of Maria. I also was not a long time, very well-established collaborator. We have one paper that we co-authored. And even though I think that Maria is one of the people who had like a deepest impact in my formation as a physicist. And I think that says a lot because I was a student of Paco, but like even just being around, like Maria was always available to talk and we could always learn with her. So thank you for that. And so we have already seen some of the style that Maria has and that it caused a big impact in me. So we already heard this, the importance of knowing where we come and where we are going. We also had like this no-nonsense approach to physics. And there is this next quote that I don't think I heard it directly. Hector told me. As all good quotes, probably it never happened, but I think it suits. It's que la realidad no te confunda, don't reality fool you. So it's true. Okay, so it's not apocryphal. So this actually said. And yeah, so this is something that I think I fail most of the times, but at least I aspire, and I think I try to influence students that I interact in some way to have this kind of approach, which is essentially kind of renormalization, intellectual renormalization. Select which ideas are important, which are not, like discard the unimportant stuff and just keep the relevant degrees of freedom. Okay. So I promised Eduardo that I had a picture with more people from this review paper on strain, which is the one paper that I have co-authored with Maria. And actually it's not, okay. We only have, so it's of these 13 authors, we just have 9 people. So Geli, Paco, Pablo, Jürgen, Alberto, Hector, Rafa, Mauricio, and Fito. And the reason I thought that there would be more people in this picture, because this meeting in 2014 was actually where this review started being organized. So we have this tentative program where you have this party session, where you have strain, various aspects, membrane, mechanical, geometrical, influence of electronic materials other than graphene. And these are basically the sections of this review paper. And I did some archaeology and also find this email from Maria like a few weeks after saying that, okay, let's start actually writing this review. I am not in this picture because I remember that from these 2 days, I was only able to attend the first one. And the second one was the more social, with the more social part. This is a picture from the first one where like we are in a work session. I'm still not here explicitly, although I think that that shoulder is me, okay? It fits, it's in the back of the room, so it's usually where I stay, where I sit if I can. Okay, so thank you, Maria, once again. And now for an important part of this contribution, okay? So I will try to convince you that in Moiré materials, such as twisted bilayer graphene, quasi-periodicity is important, okay? And again, I'm probably inadequate to give this presentation because in this research, I was the naysayer. I was always the person who said that, no, like, just looking at Moiré is sufficient, quasi-periodicity shouldn't matter, okay? But I was persuaded that it does matter, and I'll try to persuade you also, okay? So in twisted bilayer graphene, you have these 2 layers of graphene. They are slightly twisted, and you get these very pretty, visually, aesthetically pleasing patterns, these Moiré patterns, okay? And they actually control the physics of twisted bilayer graphene because they lead to a reduction of the Fermi velocity and the formation of narrow bands. Because you have these narrow bands, you have an enhanced density of states, and so these promote correlated phases and superconductivity, and people are all very excited about it. Okay. So this is a view from the Dirac cone, so we should have at least one Dirac cone. Okay. So we have here the Brillouin zone of graphene, and you know that in these corners there is a Dirac cone. Okay. But now we have 2 layers, you have 2 cones, so 2 cones double the fun. Because of the twist, they are slightly separated. And we have this intersection of the 2 cones, okay, of one layer of the other. But now there is some hybridization, and we have an avoided crossing, okay? And now, if this avoided crossing is such that this band kind of collides with this other band, this forms a narrow band, okay? So this is the mechanism by which you have a reduction of the Fermi velocity and the formation of flat bands, or at very least very narrow bands, okay? Now, the thing is that these Moiré patterns, okay, in twisted bilayer graphene, you always get an actual crystal, so a periodic structure for some angles, okay? So for M and R integer, co-prime integers, these are the angles at which the structure is a crystal, okay? The R equals 1 case is special because the Moiré pattern is the unit cell, and for any other R, the unit cell is actually larger than the Moiré pattern, okay? And for any other angle, the structure is quasi-periodic, okay? It doesn't have a unit cell. So is this important? For a long time, the answer was, people thought that no. The only thing that matters is the Moiré. If you have a model that captures the periodicity of Moiré, you have everything that is necessary. And this is what I thought, okay? But this is like evidence A that periodicity maybe matters, is in 1 dimension, the Aubry-André model, which is just a 1D tight binding chain with nearest neighbors hoppings. And we have an on-site potential with cosine modulation. But you choose a period that is incommensurate with lattice spacing, okay? And if you do this, you can get essentially Anderson localization, okay? So quasi-periodicity can induce localization of states, at least in 1D. And the way you can see it is you can do an expansion of your states in terms of block states. And if you do this, and you just replacing the Hamiltonian, you get another Aubry-André model. But now it's flipped. What was a hopping becomes an on-site term, and what is the modulation becomes a hopping. Okay, so we have this duality. If you do this transformation and you change V1 by 2t, you get the same model. And so this hints you that if V is small than 2t, you should get extended states. If V1 is larger than 2t, you should get localized states. Okay, so this is the first thing that makes you think that maybe quasi-periodicity does something. Okay, so in this talk, I'll present like 3 works that kind of build this case. We still don't know everything, most of the things we don't understand, but we are starting to get a picture that maybe quasi-periodicity is really important in this system, okay? So the first one will show that in twisted bilayer graphene, you can get subballistic behavior. Then I'll go to 1D and show that for a certain particular model, you can get quasi-fractal order induced by quasi-periodicity. And then you also see still in 1D that superconductivity can lead to enhancement of quasi-periodicity can lead to enhancement of superconductivity, okay? So the people who have been working on this, so we have Miguel is a PhD student, Hadi was a former PhD student, now he's working at Bosch. Ricardo Oliveira is a master student who recently concluded and will soon start his PhD. Flávio Rich is also a PhD student. And we have Pedro from Lisbon, Eduardo, and Ruben Mondain from Beijing. So this is a quite delocalized group, but the heroes of this story is really Miguel, Hadi, and Ricardo did the calculation, and especially Miguel. You know, he really, without his perseverance and bound energy and ingenuity, we wouldn't be able to present this. Okay, so really clever guy. So in the first case, like subballistic behavior in twisted bilayer graphene, you can read more in this. It's published already into the materials. Okay, the message is not very. It's not a very nice one, because if you want to capture quasi-periodicity, what we are saying is that we have to abandon these continuous models, and we really have to go to real space and use a tight binding model, okay? But it is what it is. It's what we did, okay? Probably it's not very smart, but it's what we did. And then we want to take, if you want to model an incommensurate structure in the thermodynamic limit, typically you want to put still periodic boundary conditions to minimize edge effects, okay? So this is hard. So how do you put boundary conditions in a system that's incommensurate, okay? So what we do is we get a sequence of angles, okay, that approach a certain value that you want it to be incommensurate, but for each angle the structure is actually commensurate, but we simulate just one unit cell so that the system never sees that it repeats itself, okay? So in this way, and by choosing angles that the unit cell size increases, we can approach the thermodynamic limit of a quasi-periodic structure. And the angle is essentially the same, so it's the Moiré pattern is always the same, okay? But the unit cell is growing. So we looked at the density of states, so this is what we see. So there is some numerical noise, but you have this, like, brighter means more density of states. And as we go to small angles, at a certain point, you get a very narrow band. Also, this is the flat band regime, okay? Just by looking at the density of states, we cannot distinguish commensurate structures from incommensurate ones, okay? But then if you want to look at localization properties, we look at the wave function in real space, and you can measure it with this inverse participation ratio, which tells you that, and you see how it scales as you increase the system size. And you know that if a state is localized in real space, the IPR should go to a constant. If it's extended, it should go to 0 with system size, okay? And when we did this for twisted bilayer graphene, we always got extended states in real space, okay? And at this point, it was like, of course, I mean, Moiré, the continuous model works. It's essentially a periodic model, so you have block theorem, the states are extended, like we're never going to get anything other than this. But wiser people said, no, let's keep trying, okay? And so we started looking at momentum space IPR. It's basically you just get the wave function in real space. We do a Fourier transform, a discrete Fourier transform, and we look at the IPR, but now instead of summing over R, we sum over K's, okay? And the picture is the same. So if a state is extended in momentum space, the IPR should go to 0. If it's localized, it should go to a constant. Just one block state. If you have a block state, you just have one momentum. And so this is what we expect for a normal ballistic metal. But when we looked at twisted bilayer graphene for incommensurate angles, so again, this is the density of state, and we look at the IPR, we see at the IPR of K, we see that in the narrow band, IPR becomes very small. And this is kind of interesting. And then we compared what happens in an incommensurate structure versus a commensurate structure. And we see that while for the incommensurate structure, the IPR becomes small, close to the narrowband regime. For the incommensurate structure, which also has a narrowband, like nothing happens. So this is quite peculiar, okay? So then we say, okay, why it seems that we only, and an important thing is that this reduction, God damn it. Okay, and we see that it only happens in the narrow band, okay? So maybe something is important to getting a flat band in this. So we also looked at that. We look at the IPR when we are at the narrow band. So this is the narrow band, okay? It's a zoom of this region. And then we looked at what happens when you are far away from the narrow band, okay? So this is at the magic angle, but we look at, not at the narrow band, at another part of the spectrum. And we look at IPR, how it scales with system size, and this is really what lets you see if you get extended states or all localized. And you see that, so outside the narrow band, the IPR of K saturates, so you get a normal ballistic metal. But if you are in the narrow band region, for incommensurate structure, the IPR of K goes to 0, saying that you have an extended state in momentum space, okay? So outside flat band, we get usual behavior. In the narrow band, for the incommensurate structure, you get momentum space delocalization, okay? So this is quite weird, but the similar, it's kind of, this is just saying that we weren't mad, like other people saw this, not just for twisted bilayer graphene, but for a whole class of models that are these so-called magic angle semimetals that are characterized by, you have some parent model that has Dirac cones, and you have some perturbation that induces a flat band, and then you make this perturbation quasi-periodic. When you have a flat band and quasi-periodicity, you have these states that become delocalized in momentum space and in real space. We complemented this calculation with some transport calculation, so Landauer transport. So this is not really easy to measure experimentally, but I mean, it's a step closer to experiment, okay? So it made us happy, okay? And here we see, so this is, I showed the density of state, so in red is for commensurate structure, in blue is for the incommensurate, and the density of state, you really cannot distinguish one from the other. But when we look at transport, in the narrow band, you see that for commensurate structure, conductance saturates, so you have ballistic transport. When you are in the incommensurate structure, it goes to 0 in a subballistic way. If you are outside the narrow band, you always get, though this will probably still have some finite size scaling, but you don't see a difference between a narrow band and outside the narrow band. Everything behaves in the same way. And this is agrees with the IPR of K scaling. Okay. So now we know that in twisted bilayer graphene interactions are important, but these calculations are already very hard, and putting interactions would be hell. So we decided, okay, let's take one step back and go to 1D. Okay, and there we can put interactions. And let's see what happens, okay? So we consider this model, which has a quasi-periodic modulation, but not of the on-site energy as the Aubry-André model, no, it's not, but of the hoppings, okay? And we also have a modulation of period 1 over tau, okay? This also induces a kind of Moiré, okay? And we choose this model for two reasons. One is that if you choose tau close to 1/2, close to 2, sorry, you get narrow bands, so similar to graphene. But differently from the Aubry-André model, where you have a transition from extended states to localized states, here you have a transition to critical states, meaning that states that are delocalized in both momentum and real space. So this is the closest thing we could come up that models twisted bilayer graphene in 1D. So narrow band with momentum delocalized states. And I won't talk much about here, just advertise there are these 3 series of papers from essentially Miguel. He came up with it, and it's basically an RG procedure based on dualities that allow you to determine localization phase diagrams with very high accuracy, many times analytically. Basically, every model that we see in the literature is methodology works. Okay, so really interesting stuff. I invite you all to check these papers. And again, this is all from the mind of Miguel. Okay. Then we put interactions in this model. We consider spinless electrons at half filling with a nearest neighbor repulsion. Okay. And because this is 1D, we can do the MRG. So completely unbiased calculation, we are only limited by numerical accuracy. And so we looked at the phase diagram, and we compared an incommensurate system with a commensurate system with this tau close to 1/2. Okay. So this repulsion, nearest neighbor repulsion, for large enough U at half filling, we guessed that these ones, one side to be occupied, empty, occupied, empty. So it should induce the pi charge density wave, and this is what we see. And for small interactions, we should get a Luttinger liquid behavior, so a gapless system. Okay, this is what we get. And now we turn on the incommensurate modulation of the hoppings. And if you look at the region where you have extended states, like both diagrams, they are essentially the same. You have a Luttinger liquid in one side, and the other side you have a charge density wave. Now you can have modulation at several momentum, not just one, so we call this a Moiré charge density wave. There are some small differences between commensurate structure and incommensurate, but it's really hard to distinguish. Okay? And there's a phase transition separating both. The interesting thing happens when you go with this region, when V2 is greater than 1, which in incommensurate system you get these critical states. Okay? In this regime, it's really interesting because the incommensurate system, you get still a Luttinger liquid state, and then a phase transition as you increase U to a charge density wave. But in commensurate case, this Luttinger liquid phase disappears, okay, completely. And what we get is a weird charge density wave, which has order at many wave numbers. So we called it quasifractal charge density wave. And separating these two regions from the quasifractal charge density wave to the Moiré charge density wave, we don't have a phase transition, but we have a crossover. Okay, so quite different behavior from. And this is really just same system, very similar, just commensurate or incommensurate one. So how we draw this phase diagram? The primary quantity that we looked at was the modulation of the charge. So we have the local charge density. We do a Fourier transform, and then we did an IPR. We defined an IPR for this quantity. Okay, and what this IPR tells you is that if the IPR scales to a constant, you have a charge density wave. So we have a single wave number charge density wave. This IPR is 1. If you have order at several wave numbers, it's a number smaller than 1, but it saturates in the thermodynamic limit. In the disordered phase, this IPR should go to 0. Okay. And so this is a regime where you have these extended states and you turn on the interaction. You see that for small u, the IPR goes to 0, and you have a disordered phase. You increase u, the IPR becomes finite, and you have a charge density wave. Okay. And you can have charge density wave as several wave numbers, not at just one, okay? And the only difference is that in the commensurate system, you can get order at, you can get a charge density wave at wave numbers which are not allowed in the commensurate case. But if you just look at the picture, it's very small. It's very hard to distinguish both systems, okay? Now if you go at the critical states, it's more interesting, because if you go, now you look at this IPR as a function of U, and if you are a very large U, so again, green is incommensurate systems, quasi-periodic system, red is the periodic systems, okay? And for large U, it's basically the same. But as you lower U, you see that the IPR seems to go to 0 in slightly different ways. And for the commensurate case, there is this abrupt change, so it seems that there is a charge, a phase transition. In green, it doesn't seem to appear you don't have a phase transition. So we looked at the fidelity susceptibility, which tells you how the ground state changes as you modify some parameter. In this case, the parameter is U. And then indeed, you see that for the commensurate case, you have like this divergent of susceptibility at a certain value of U, indicating that you have a phase transition. For the incommensurate system, you never see a phase transition, just see a bump. So an increase in susceptibility, but it saturates with system size. So it's not a true phase transition, it's just a crossover, meaning that in the incommensurate system is always in the same phase. Okay? So it starts with a charge density wave here, and as you lower U, there is never a phase transition to anything else. It's always a charge density wave. And indeed, again, it seems that the IPR goes to 0, so it seems that it goes to a orderless phase. But if you simulate very large systems, you see that initially the IPR goes to 0, okay? But then eventually it saturates. And this is really what's showing that you are still in the charge density wave, okay? Just the charge density wave that there's order at many vectors. So I'm just showing what the order looks like. So you have this susceptibility. You are in this region where both systems should be in the charge density wave. The pictures look very similar. You lower U, and you look at this point where we already have the crossover in the commensurate system to the fractal charge density wave. So you start getting order at many, many wave vectors. It starts getting like a very noisy picture, okay? And the commensurate case, you still have a Moiré charge density wave, so meaning that you have order, but at only very specific wave numbers. And then if you continue lower U, the commensurate system, goes into the Luttinger liquid phase. So you have these peaks here, but actually if you squint, you see that as you increase the system size, these peaks decrease. So it means that this order is vanishing as you reach the thermodynamic limit. While in the incommensurate system, you get order like at basically all wave vectors. Okay, but so it's still a charge density wave, and the peaks of these orders like they saturate. Okay. So here you have a case of order that is stabilized by quasi-periodicity. Okay, that it doesn't exist if you don't take into account quasi-periodicity. And finally, we have an additional, another proof for this case that we are making, which we also see an enhancement of superconductivity in 1D critical systems. Again, what we really want to do is look at superconductivity in twisted bilayer graphene, but you know, we eventually will get there, but it's just complicated. So we look at this generalization of the O'Brien-Day model. So the O'Brien-Day, you have a modulation of the on-site potential. In the previous model, you had a modulation of the hoppings, and then we consider both things. So this makes a localization phase diagram that is richer. So we have like extended states, so when V2 and V1 is very small. If you increase V1, you get a localized phase. If you increase V2, you get a critical phase, okay? So this gives you a bit more freedom to play with things, okay? And then we do the BCS mean field theory, even though we are in 1D, okay? You just want to see what happened. And we see that quasi-periodicity leads to an enhancement of critical temperature, particularly if you look at the localized phase or at the critical phase. So here we have like 3 curves. So the blue dots, it's for a commensurate system. The n equals 1, so these green dots are for the quasi-periodic system. And these golden squares is an intermediate case. So it's a periodic system, but with a unit size that is larger. And what we see is that as we go from the fully periodic system to the fully quasi-periodic system, the critical temperature increases. Okay, so we see both in the localized and the critical case. So we see this as a hint that quasi-periodicity promotes superconductivity. And we also look at this, so the pairing now, it's not homogeneous, but we can look at, in real space, but you look at its maximum value. And so this follows the same behavior as the critical temperature. And again, we see an increase of this max pairing as you go from the commensurate structure to the incommensurate one, like further indicating that quasi-periodicity is enhancing superconductivity. Okay, so for these conclusions, I hope that I convinced you that quasi-periodicity plays a role in Moiré systems. So we saw that in twisted bilayer graphene at the single particle level, it induces subballistic behavior. In 1D systems, quasi-periodicity can stabilize new non-trivial ordered phases. It also enhances superconductivity, but we still have many open questions. One is phenomenology. What can we tell an experimentalist to measure that you'd be able to distinguish what is a quasi-periodic system from a periodic one? We still don't have a very good answer, even at single particle level. And another one is like this ultimate goal. So we really want to do twisted bilayer graphene. So we want quasi-periodicity, flat bands, interactions, and 2D what happens, we don't know. But we are trying to get there. And thank you for your attention.
Thank you, Bruno, for the talk. So it's open to questions or comments.
Bruno, I have to ask this. Thank you very much for your words first. And then, as you know, I always stop in the first slide, first sentence. So aren't you worried by the fact that the real space and reciprocal space gives you completely different results on localization?
You mean because in real space they are extended, and in momentum space they are also extended? This seems to be a contradiction. Mm-hmm. Yeah, I also worried about that. It's not a fully satisfactory answer, but at least I could sleep with it. And so this Fourier uncertainty principle, you need to have normalizable states. Okay. So it only says you that if you have a state that is more localized in momentum space, it will be more extended in the dual space. Okay. But if you are working with non-normalizable states, I think this is the loophole for this Fourier uncertainty principle. We know that for a plane wave, the Fourier transform is a delta function, so it's fully extended, fully localized. But then with a delta function, you cannot compute what is the expected value of the position with sandwiched between two delta functions. So I think that this is the mathematical loophole that allows you to get states that are delocalized in both bases. Okay. This doesn't tell me why it happens, but at least it says it's not mathematical inconsistency. And because other people have also seen this, it's like, yeah, maybe it's not wrong.
Yeah.
Thank you for your work. It's beautiful. I have two questions. First is the question for the commensurability is for rigid systems. Are you taking into account relaxation?
That is a good question. We never took into account relaxation. We think it doesn't matter. Because even if you have a structure that is quasi-periodic and you let it relaxed, it will still be quasi-periodic. So at the Moiré scale, there will be some reconstruction, but the structure overall will still lack periodicity.
Okay.
So we think that our results will be robust to that. We didn't try that. For the twisted bilayer graphene, we tried so we have quasi-periodicity and we add Anderson disorder on top of it. And the results are robust against Anderson disorder. So this gives us some hope that even if you have this twist angle disorder that people see in experiments, that maybe these results are still apply. Because what is really important is quasi-periodicity or not. Is it periodic or not? Those kind of reconstruction is a detail and it doesn't change the underlying fact that the structure doesn't have a unit cell.
Okay. And only one observation. Probably instead of the inverse participation ratio in the momentum space, I'm not sure if it's complicated. Why don't you use instead of that the trace of the quantum metric? Because can give you the localization. I'm not sure if it's possible to.
One of the works we did, right? But not in these ones. So we have another work that's actually already on archive when we do look at that quantity.
Okay.
In 1D, yeah, in 1D. For the twisted bilayer case, we didn't look at that.
Okay, thank you.
We were happy with the IPR and the Landauer transport that they seem to indicate the same thing.
Thank you.
Thanks. Thanks, Bruno. Very cool results.
Thank you.
Do you know, like for the last part, there's this enhancement of TC due to multifractality of the wave function.
Enhancement of?
TC.
TC.
Yeah. So I wonder if this is something new or is this related to this?
So there were also a couple of papers that also saw this enhancement of superconductivity in 1D and also in 2D. What we did, it's it's epsilon nu, but it's in this system, this region with critical states, where you have, it seems that it enhances even more the superconductivity.
No, I guess I'm referring to some works of Merlin. I don't know when, but like some years back.
Okay.
Like
no,
way before.
Okay, I'm not aware
Twisted
of
by
that.
Layer and stuff. There's some works where if you're close to the mobility edge and your wave function is multifractal, you can enhance DC due to the Zohar.
Okay.
And so I was wondering whether this is kind of
Okay,
related
so maybe,
or not.
yeah, okay, okay. I'll ask you to send me those references because it seems relevant. Thank you.
I have just maybe a very simple question. This inverse participation ratio is basically a scalar characteristic, so it shows you how many lamps are around and how they overlap together. But do you have some vector characteristic, for example, in principle, those structures, they can, they can form some non-trivial, they can be non-trivial, linear structures, so say two-dimensional one. Okay, in your case, it should be linear, because you should be able to characterize, say, for example, disconnected lamps with this, say, linear dimension 1.
I guess that if you are in 2D, if you have these kind of states that are extended in one direction, this would show as how it scales to 0. Yeah. So if it scales to 0 with the area or with the linear dimension of the system.
I see. So you can see that in this year, you had L squared.
Yeah, if it scales down with 1 over L or 1 with 1 over L squared, it should tell you if you have a localization in a spot or in an extended line.
Okay, thank you.
You're welcome.
Thank you. Any further questions or comments? Okay, that's not the case. So let's thank Bruno and Luis Bonilla once again. And the session is closed.
Welcome everyone to the last session, Geli as a mentor. Our first speaker is Miguel Ángel Moscoso from Carlos III. So the floor is yours.
Okay, thank you very much. Good morning, everybody. Okay. So again, thank you very much. Good morning, everybody. I see Geli right now staring at me, thinking to herself, Miguel, how did they get you to do this? We talk about it. The thing is that Belén called me. She told me Geli was retiring, and she wanted me to say a few words about what Geli's time at Carlos III meant to us. The first thing that came to mind was that our Geli could not, in fact, retire. She is too vital of a person, and I have no doubts that she will continue working towards a better world, a fairer and more beautiful world, which is what interests her. She's interested in people. She's interested in human warmth. I believe that is what she has dedicated a fair amount of her life to. She has worked for science. She has worked for science in capital letters, to be more humane, to help us learn from each other, even if it was just for the sake of having a coffee together. Regarding her students, she has not only been interested in bettering their work, but also them as people. Miguel, yesterday, so-and-so told me blah, blah, blah. I have told him no. Things have to be done. Well, right, Miguel. If you don't do things right, they come back to you sooner or later. But they grow, and they come back to you bigger. She has guided me with similar saying when it was necessary, although she might not remember it now. She has been a strong and very positive support for me. She has never understood the teacher-student relationship the old-fashioned way. She thinks of students as equals. And Geli listens. She listens a lot. She has also learned a lot from her students. And that is something her students know. I see some young people over here staring at me, thinking to themselves, don't be cheeky, Miguel, you are not one of her students. Well, they are right. I'm not her academic student, but I feel like one of them. I have learned, and I keep learning a lot from Geli. In fact, when Belén asked me to speak about Geli at today's event, I told her, please put me at the end with all the students. Also to feel younger, of course, to be honest. But let's get to the main point, what brought me here today. What has Geli time at Carlos III meant to us? Her wonderful, almost 11 years with us at our university. Of course, she meant many things to us: honesty, hard work, companionship, happiness. Overall, she's a friend. A friendship that fiercely lasts still to this day. There is a car scrapyard, a place where you bring the old cars to wreck and smash it to pieces. This place is on Toledo Highway, 25 kilometers from Madrid, and it offers spectacular menus for only 16 euros. And it's close to our place, to Carlos III. We will be going there with Geli once again in a couple of weeks. And you are all invited to join us if you want. Anyhow, what has Geli time at Carlos III meant to us? What is in between a teacher and a student, Geli? Miguel, we have also spoken a lot about this. Between a student and a teacher, there is only a piece of chalk or a marker nowadays. Miguel, remember that. But Geli has taught us that between a teacher and a student, there is mainly respect. That is one of the most important things we have learned from her. Geli has shown us the importance of respect. Respect for students, respect for colleagues, respect for the work we do. Respect for the work well done every day. Thank you, Geli. We love you. See you at the scrapyard. Thank you very much. I guess no questions.
Thank you. Thank you, Miguel.
Thank you very much.
Yeah. Okay. Well, let's take Miguel again. He's not accepting questions. Our next speaker is Yago Ferreiros.
This is probably going to be my last talk, at least in a workshop about physics. So I'm no longer a physicist, or maybe I have to say you are always a physicist, but I don't work in physics anymore. Since a few months back. Now I'm dedicating myself to other matters. So I'm not going to talk about physics per se. This is about Geli anyways, so I'm going to talk about my relationship with Geli, my professional relationship with Geli, right? So Geli in the good and even better, right? Okay, so my relationship with Geli is good, it's very good. Let's say that the affinity has not always probably been this good, maybe. It could only get better, okay? So let's say it started a little bit more slowly. But, you know, it kept getting better. I have to say through humbling experiences, humbling for me. And now it's at an historical best, right? So affinization flow diagram, just straight line, very simple, from worst to best, okay? So I met Geli when I was searching for a PhD. I think it was Paco who introduced me to Geli, if I remember well. So I think Paco thought that my background as in high energies was quite fitting for what Geli was doing and the way she worked, and I think rightly so. So I searched at Geli's work, and So I thought, wow, I really want to work with her. She's doing things, very amazing things, and she has this approach that I think I kind of share, right? So, I met with Geli, and she told me that if I wanted to, there was a PhD position for me, and I said, of course, I said yes, and I think I had the suspicion that previous work that I did with Tony was probably key to getting the position. Geli has Tony in a great regard, not only as a friend, but as a physicist, and I think also rightly so. So yeah, then, okay, so I said yes, so I started the PhD, right? So then it came time to have the first discussion about physics with Geli. And it was about graphene, and I have to say it was difficult. It was a humbling experience for me. So at the time I was young and inexperienced, and I thought I knew everything, which I didn't, of course. And those of you that know Geli pretty well know that that doesn't go very well with her. So yeah, it was difficult, humbling experience for me. So let's say that, affinity could be better at the start. An all-time low here, right? It could only get better. Okay, so then I kept working in my PhD, and I had been playing around with magnetic stuff, which for some reason Geli didn't like and doesn't like to this day. I tried to get her into these things, but I couldn't. But eventually we got our hands on biosemi-metals. And I think this was a big thing for us, at least for me. This is probably has been the main topic of my career, science. And I think the thing about biosemi-metals that we like so much is that they are a very nice match for the physics as we understand them. So, we have this high energy physics background, and all these things, all this very neat and clean physics, quantum field theory, quantum anomalies, topological stuff, universal responses. These biosemi-metals are a very nice playground for this. And I think this has been actually my most cited paper. And I think this has opened me some doors. This is the first paper I think I published with Maria, with Geli. So affinity here was already quite good. Yeah, it was good. It was much better than at the beginning, but of course it could get even better. But quite good already. So then it came time to do the defense of the thesis, and I really wanted to keep doing research full time. So I didn't really want to write down the thesis. So what I wanted to do is a compendium of publications, which is a possibility here. And to my surprise, Geli was fine with this. At the time I thought, okay, maybe she's getting old because, I'm surprised. But no, seriously, she was fine with it. She was fine with me pushing her into, keeping researching and just don't get into this, writing the thesis stuff, which can be quite long and can take you out or off doing research for some time. So I have to thank her for this. And then it came time to do the thesis presentation for the talk of the defense. So when I was doing the presentation, I remember thinking, this is quite a good presentation. I think Geli is going to like this. So then I presented it to like a few days before the defense. I presented the talk to Geli and Alberto, which is my other advisor. And yeah, another humbling experience. I don't think there was any single thing that went through Geli's filter, probably. So I had to do everything from scratch again. It was tough, but I think it was worth it at the end, because I think this has probably been the best presentation I have done in my career. So I have to thank her again for this humble experience, but worth it, for sure. So it came time to go away for my first postdoc. And during this time, I did some works with Geli. But the one I want to highlight is this one, just for two reasons. This is my only work with me and her as authors, with only me and her as authors. And you know, I finally got her because it is about magnetic stuff, right? So, but you can see that it wasn't that hard to get her because you see here elastic gauge fields, you see the word Hall. Anywhere you see the word Hall, Hell is going to like it. So, and if viscosity is after this word, even more. Also Dirac and Magnus, this last word, who cares about it, right? Small last word, right? So who cares? So very nice. Magnetic stuff work, very nice. Then I came back to Madrid for my second and last postdoc. And, and here affinity was already at an all-time high, was very good. And I think, so we published this review paper, which I think was very timely, because we published this not long time ago, quite recently. And I think this has been very timely because this has put a very nice brochure into my professional relationship with Geli and into my career. And it has put a very nice brochure because this is, you know, I think this review contains probably all those things or all that view of physics that we share and that has united us. So the thing about understanding physics, you know, through these lenses probably that came from our high energy background, you know, this quantum field theory, anomaly geometries, topology, all these things, but applied to mundane matter. So, and how, you know, mundane materials can know about these very theoretical things, right? So I think this is something that has been key, at least in my career, and I think Geli is in Geli's career as well, and is what she really likes about this. And for that reason, I think this has been a very nice brochure to our relationship. So Geli made my once a dream of working as a physicist possible. I will always be in debt to her for this. I learned plenty of physics from her, but what I especially learned is how to deeply understand the concepts behind the technical details. So Geli doesn't like technical details. I can say it probably harder. She hates technical details. But she's very, very good at going deep into behind these technicalities, going into the concepts behind the physics, the full picture, right? So this has been very important for me. She taught me how to structure the knowledge in my head. So there is a very famous sentence from her that probably all her students know. So it's a question, is from where we come and to where we go. So she always says that if you are able to answer these two things, then that's the way to structure the knowledge in your head and to do a presentation or just, you know, to have the full picture of the things, right? So this has also been very important for me. And perhaps the most important thing, Geli taught me life lessons, quite a few. And the thing is that she does this by making you, in this case me, painfully aware of my own shortcomings. So I think this is a talent of her, a very nice talent of her. It can be quite tough, but I think it's very, very important, especially for students and for people who is growing up, right? Because when you are a PhD student, you are really growing up as an adult also. So probably this is the most important of all the points. So for all this, Geli, thank you so much, and thank you all for listening.
Thank you.
Any questions, comments?
Any questions or
any comments?
I have a technical question.
What about the squatting?
What are the nonlinear corrections to this? Are there nonlinear corrections to this curve?
Which curve? Probably.
No, any more questions or comments? No. Well, let's thank Yago again.
Thank you.
So first of all, I would like to thank you for allowing me to participate in this Geli Fest. I am pleased to say hello and to be here because I wanted to to participate in this event. I mean, I'm sure that Geli will be all the time around us. And personally, I have to say, I know her. I knew her many years ago when I was doing my PhD in Material Science Institute. I have not been an academic student of her, but I have to say that in the academic life, I've been inhaling a lot of her personality. She was, by that time, at Carlos III University, and I was, as I told you, doing my PhD. And she used to come, she used to start in collaborations, I think. As I told you, I was not even in her field. And I remember those times when I shared the time with her. We usually went for lunch, and we were usually talking about everything, of course, of science, but from a free way. I mean, we were just discussing about topics without a focus ideas or focus. We were also talking about other aspects of life, like, for example, politics and anything that was funny for lunch. And I remember by that time, I remember learning things from her personality. I mean, I am younger than her now. I'm not that younger, but for example, we used to talk about what we now call feminism, for example, ideas that she was talking to me or to the people that were by lunch, and that were very interesting for life, as I told you. So after those times, I mean, I've always been in touch with her and with probably some of you in the audience today. And I have to say that she was the person I used to contact when I needed advice for many things. I mean, not only for science, but for I appreciated her opinion in overall. So in my participation here, I just wanted to say thank you for sharing her time with me, for being open to discuss everything from sometimes from a vehement way, but always sincere, always frank. And this is something that I appreciate a lot. And I just wanted to say thank you and to let you know that I'm happy to have been sharing my time with Geli. As I told you, I don't have slides. My field of work has always been different. I've been working doing theory in the Department of Condensed Matter Theory, and also in other institutions. Now I am in Valencia, and I've been working also doing experiments. But I haven't signed a paper with her, in fact. So, but even though I think that these kind of things are important, because when you are retiring, you don't always want to remember only about science, but also about other things that you have projected to the people that you have met. So I think that for me it is important that you remember me from these aspects, and to say thank you again. So this is all I have to say. I don't think that you have questions about this participation. Thank you again.
Thank you. Okay. Okay. I don't see any questions. Nothing controversial. Thank you, Ricardo. Let's thank him again, as usual. We're gonna watch a few short videos of something I found on YouTube. Oh. Okay, sorry. Okay, so actually Hector was. It's all right. I think we can watch this one first. Yeah, it's all right. So yeah, Vicente couldn't be here, but.
Hola María, buenos días a todos. Antes de comenzar me gustaría agradecer a Belén por darme la oportunidad de participar en este homenaje. Para mí es un grandísimo placer formar parte de este evento. Tuve el privilegio hace unos 7 años de iniciar el doctorado con María y no podría estar más contento de la decisión que tomé. Existen pocas personas que posean sus conocimientos, su claridad, su forma de entender la física y la investigación académica, y que además puedan transmitir estos conocimientos de una forma clara y concisa. Pero María no es solo una magnífica investigadora, sino también una gran tutora y directora. Para mí es un gran orgullo poder decir que fui alumno suyo. Me resultaría imposible poder resumir en un solo vídeo la cantidad de física que aprendí gracias a ella. Pero me gustaría destacar un elemento que guardo con gran valor y que me ha ayudado muchísimo a lo largo de estos años. Por encima de los conocimientos, María me enseñó el significado de ser científico, observar y analizar con actitud crítica, profundizar en los temas e interiorizarlos hasta comprenderlos realmente. No hay que conformarse con la explicación más sencilla, o un conocimiento superficial que simplemente permita sacar adelante los trabajos. Un buen científico debe estudiar e investigar de forma rigurosa y crítica, así como ver más allá de lo superfluo y entender los verdaderos motivos detrás de una teoría o una explicación. Mis múltiples visitas a su despacho y las preguntas que me realizaba me mostraron que no basta con saber una respuesta o conocer un tema. Lo verdaderamente importante es entender realmente los fundamentos de lo que estás estudiando y no estar satisfecho hasta conseguirlo. Eso es lo que diferencia a los buenos científicos. Y María me inculcó estos valores y hábitos desde aquel primer ejercicio que realicé al iniciar el doctorado. Algo tan simple como el cálculo del tight binding del grafeno y que ella habilidosamente aprovechó para comenzar a sentar estas bases. María, durante 4 años me formaste como científico, investigador y persona. Me ayudaste a confiar en mis capacidades y me guiaste a encontrar mi propia forma de trabajar valiéndome de mis virtudes. Gracias a ti pude aprender lo que es la verdadera ciencia y me enseñaste esta actitud científica que me acompañará siempre. Cualquier logro que consiga de ahora en adelante será gracias a ti. Por ello, María, muchísimas gracias por todo y muchísimas felicidades.
Okay. Hi everyone. Hi Geli. Happy birthday. This is kind of awkward because I'm alone in a room in my apartment. But you know, this is happening very early and I wasn't sure that I will, wake up for the session, but still I wanted to say something about Geli. So Geli is one of my favorite people in the world. Basically because of 2 reasons. The first one is because Geli is a lot of fun. It's a lot of fun to be around her. It's a lot of fun to have a conversation with her. Yeah, and the second reason, and I guess that's the topic of this session, is because I learned a lot from all these discussions with Geli over the years. And I guess that's what it means to be a mentor for someone. When you learn stuff from somebody that, otherwise you wouldn't learn, right? So, I mean, I could tell you a lot of stories, or I don't know, I could give you a list of things that Geli did for me and for other students in Madrid. All the courses that she organized, we all learn RG from Geli. But rather than just give you a list, I think I can just give you a summary of the things that I learned, or at least one thing that I learned from Geli, and actually it took me a while to understand, and I believe now I understand better what she meant at the time. But it's a sentence, it's something that Geli, I'm sure she told me several times, because, you know, I'm sure she told me directly to me, but I cannot remember exactly the situation. So I'm sure she repeated this to other people. So maybe this sounds familiar to you. But the sentence, and is a very, this is the very typical witty style from Geli. The sentence is, no dejes que la realidad te confunda. Don't let reality confuse you. This is something that Geli always told me, discussing, I don't know, stuff on the blackboard. And at the beginning, I always thought, like, what the heck, what is this woman? Why is this woman telling me this? What's the meaning of this? And I just realized with I don't know, the pass of time, I guess, that actually this is a very valuable lesson because it's what really physics is, and what really doing physics is there is nothing more unnatural in nature than natural laws of nature. They are not written anywhere. The only way you can figure out something is if you look at the thing with the right glasses. And I think that's what always Geli meant by you know, don't let the reality confuse you. Is that you really need the proper framework, the proper vision, the proper way to think about stuff when you are like facing a physical problem. And she did that. I mean, she has been doing this for many years in her career, and is famous for that, for applying field theory techniques to condensed matter problems. We all learn this way of thinking about physics and condensed matter phenomena from her. It's now it's kind of more, I don't know, popular or well accepted among solid state physicists. But I guess when Geli transitioned from the dark side to solid state, this was not that common. And actually, within the Spanish landscape of solid state physics, I will say this was really, I don't know, exceptional. And I think we should all value that, because we learn a lot of stuff from Geli, things that otherwise will not be, I mean, accessible for us, at least in Spain, I would say. And yeah, and that is great. And that's one of the, I don't know, when people say I'm lucky, yeah, they are probably referring to situations like this, to have the chance to be close to Geli. In my case, you know, she was never officially in any official capacity as a, you know, PS advisor or something like that. And still, she was always around and helping me out and giving me these kind of lessons. I think they are important, and now I'm trying to transmit to younger people, I guess. So anyway, so that's what I wanted to say. I don't want to talk too much. This is kind of weird, as I said before. I'm alone here in my room. I hope I was here, I was there. And I don't know, Geli, happy birthday again. We'll see you in a couple of months, I think. And I don't know, have fun. See you.
Can I ask whether someone in the Zoom can say, if they want to say a few words? I don't know if there's...
Emmanuel? Oh, Manuel.
Hi, sorry. I spent some minutes trying to how to write the message. And okay, I apologize because for family reasons I didn't manage to follow all this meeting, but I'm here. And I would like to thanks a lot, Maria and everyone. I spent 2 years in Madrid. They were wonderful years for physics, very fruitful. And for life, I felt at home in a family. And this was really also a big share because of Maria. She was really, really wonderful job there. Organizing talks and discussion, we really felt really in a family. I have two regrets. One, that when I came to Madrid, I was already old, and for me, Maria was a big name in literature, so I knew her from literature, so I never managed to switch to the confidential name, Freddy. So I still keep on calling her Maria, but this doesn't mean that I feel really attached to her. For me, it meant a lot. And the other regret that we never managed to publish something together. I remember one summer in Santa Barbara, we spent a lot of time brainstorming with Hector and Vito. We almost had the draft, and then we realized that there was a flaw in how some data from Evandre were stored, so all the results were biased. So we never published something, but this, for me, still, she played a big role in my life, and I always saw her as a big physicist and a big teacher. She was really teaching physics and life and friendship to all the people there. And when I was there, I learned Spanish. I was speaking Spanish, and teaching is enseñar, which is the same word as much as I remember, then showing, making visible, which is the same activity, the art. So in the end, I think she still continues to do the same activity. Thank you, Maria. Thank you, Harry.
Estimados participantes en el Geli Fest, querida Geli, en primer lugar, quiero agradecer a los organizadores de esta celebración la invitación a participar. Lamento no poder asistir en persona, pero me ha resultado imposible cambiar los compromisos previamente adquiridos. En cualquier caso, es un placer estar aquí y un honor poder contribuir, aunque sea desde la distancia. He estado tratando de recordar cuando conocí a Geli, y creo que fue al comienzo de los 80, seguramente en los descansillos de nuestro querido C11 en la Universidad Autónoma de Madrid. Yo era entonces un recién licenciado y ella una prometedora doctora. Eran tiempos de sueños y esperanza y sobre todo tiempos de pasión por vivir y por la física. Geli, tú te fuiste a Israel y yo a Estados Unidos, pero el destino nos reencontró en Princeton en la segunda mitad de la década de los 80. Contigo, con Ángel, con Clara, no nos faltó de nada. Consolidamos nuestra amistad, trabajamos juntos, nos asombramos por lo inaudito de la naturaleza y hasta hicimos nuestros pinitos literarios. ¡Qué tiempo tan extraordinario! Luego, la vida y la profesión nos llevó por distintos derroteros, pero hemos mantenido nuestra amistad, sabiendo que nosotros y nuestras familias estábamos siempre ahí. Hemos visto crecer a nuestros hijos, hemos madurado y nos hemos reconfortado con nuestros análisis y nuestras visiones de lo que nos ha ido rodeando. Es un honor haber recorrido todos estos años contando con tu amistad. Quiero transmitirte mi felicitación por tu trayectoria como investigadora y así unirme a esta celebración. No voy a hacer una referencia a tus aportaciones científicas porque hay otros participantes que sin duda lo harán mucho mejor que yo, pero sí que quiero decirte que he seguido tu carrera con admiración. Una admiración que no se circunscribe únicamente a tus trabajos científicos, sino a todo aquello que has aportado a las muchas personas que te han rodeado. He experimentado lo que es trabajar contigo y he oído a personas hablar de lo que ha significado para ellas. Debes estar orgullosa por haber contribuido al desarrollo profesional de numerosos investigadores. También quiero transmitirte mi felicitación por haber materializado una carrera profesional como científica tan extraordinaria, a la vez que has desarrollado tu talento en el ámbito artístico y has mantenido tu pasión por las humanidades y en particular por la literatura. No es fácil encontrar personas tan completas y esto multiplica mi admiración. Hemos disfrutado mucho con tus pinturas y de apasionadas conversaciones sobre lo humano, a menudo con tus toques literarios, siempre muy enriquecedores. Todo ello me proporciona una sana envidia porque te posiciona en una situación única para sacarle todo el jugo a la nueva etapa que ahora comienzas. Seguro que nunca te sentirás abrumada cuando te sientes a la mesa y alguien venga con la famosa pregunta "What are you doing these days?", con la que nos retaba un famoso personaje en el comedor cuando estábamos en Princeton. Al igual que entonces, seguro que tendrás una extensa respuesta que dejará a todos asombrados. Finalmente, darte las gracias por todos estos años de amistad y desear que la disfrutemos durante muchos más. Te deseo que disfrutes mucho de esta celebración.
Permitidme dar las gracias al Departamento de Comunicación, que son increíbles en todo lo que han hecho para que esto sea posible. No solo su profesionalidad, sino su ánimo, su alegría, en fin, fantásticos. Y el vídeo lo ha hecho el mago Morgan, o sea. Y la página web aquí. Bueno, y muchísimas gracias a todos por participar. A todos los que habéis estado en ponencia, a todos los que habéis venido a escuchar. Y ahora, Geli, te toca a ti. Por favor, venid de todos los organizadores. Subir allá, como quieras. I feel better here, which is a place that I've been occupying very often. Still, I'm shocked to see why I'm here and not there. Anyway, seeing these pictures and these last contributions, I realize how lucky I've been. And I've seen a couple of things that I'm particularly thankful to. Yago is the only one who has had the courage to suggest that there were times not so good in our relationship. Thank you very much, Yago. It was hard also to me, but I'm so happy now. And I know that many of you, not only Yago, went through, not you, but through a bit more difficult times, because I'm not an easy person. Bruno also suggested it a little bit. And I thank you very much for having, Vito here, for having swallowed all the hardness that sometimes I threw on you and converted it into positive things in our lives. I've seen also how much accompanied I've been in all this professional life. That has, of course, been a lot of fun, but not just because of me, but because of you. I mean, the sense of humor, the life, I mean, that you all meet, and the generosity that you have had, all of you, to accompany me, an old person, you know, in all these ways. That has been wonderful. Listening also to Hector, I've seen another thing which I always suspected. It is not this syndrome that all the women have, that imposter syndrome. No, it's not that. It's a reality. It's that happened to me in Princeton, that happened to me when I talk to you. It's the way that you throw some thought that you don't know really where it goes, and immediately comes back from very bright and generous persons as you, in the form of a wonderful suggestion, you know, and then you're shocked, say, did I say that? That happened in science a lot, and that happens also in life. So sometimes you just say something that you don't know exactly what it means, and it comes back in the form of an enormously fruitful and enjoyable thing. So what else can I say? Thank you very much. All of you are younger than I, with one exception, 2, 3. Okay, no, 2. And 3. And have accompanied me for my entire life, you know. And I really thank you. And I think that maybe I did something in your lives, but you certainly did a lot to my life. And thank you very much. That's my first product, professional. I'll be always proud of her. Thank you, Belén. And that closes the thing, I hope, because I cannot cry more. Well, I don't know, a little bit more maybe. So if you come here. the organizer. You're going to sing? Well.
Oh, yeah. We have a song. Eduardo is the lead singer. It's a father.
Start with the father we have over there.
Si vais a decir algo, utilizar esto. Vale, eso es omnidireccional.
So, it's do you believe in Santa Claus? Okay, a very special one. Okay, I start. Let's. No, ¿cuál? Este? Okay. Okay, who claims this?
No.
Carl, you're the deliverer. Sir, reindeer Carl. I think it's probably appropriate to open it in public.
Oh, yeah.
It's
So you're prepared for this weather.
Yeah, exactly. The heat wave. It's.
In case that somebody wants. Este es el más cachondo y este es el más.
Okay. So let's finish with the. Maybe this one. Okay.
Thank you.
Oh, it looks very nice. I think that should be your official uniform from now on. Oh, there are more. Sorry. Okay. Please.
No tienes tu duda.
No, everybody. Very good. Now you have everyone. Yes. And yeah, it's. It's a book. No, I'm just joking. Oh, maybe. Yeah.
No es fácil. No te lo fácil. Hay unas llaves.
It's like a strain won't help you here. Yeah, you need some face transition.
Right.
Yes. Blackboard. Or to take it wherever you go.
Yeah, that's right.
May or may not. May or may not be chalk.
You see, that's what is important here is that not too many details can be put.
Exactly. It's just the right questions. Exactly. And chalk, yeah. Important.
Thank you very much.
Yeah, it's not. We're not finished. One more. It's not everything is about physics. Oh, and there's. You know what it is? Yeah.
It has my name on it.
Yes.
That's to hold the brush when you talk.
I think there's one little, yeah.
writing.
Exactly, exactly.
Thank you very much.
Yeah.
And now, yes, it's closed. Thank you.
Yes.
Gracias, Eduardo.
Forgot the.
Thank you all very much.